Hello students, today's question is which of the following is an eigenvalue of the matrix 5 0 0 0 0 5 0 0 0 0 2 1 and 0 0 3 1, and we have given four options. Option A is the vector 1 minus 2 0 0, option B is 0 0 1 0, option C is 1 0 0 minus 2, and the last option is 1 minus 1 2 1. First, let us revisit what is the eigenvalue and which are the corresponding eigenvectors. So what do we know about the eigenvalues and eigenvectors? If we have given any n cross n order matrix A, then it has non-zero eigenvector x if there exists a scalar lambda. Which kind of scalar? Which satisfies the relation Ax is equal to lambda x. So this is the first equation. We have Ax is equal to lambda x, and this equation leads to this determinant of A minus lambda I is equal to 0. This is the another equation. Determinant of A minus lambda I is equal to 0. Now this equation can be rewritten as A minus lambda I. A is order n, so this is identity matrix of order n, into x is equal to 0, and this 0 is the matrix of order n cross 1. So this is the third equation. So these are three important equations here. The first one is x equal to lambda x. Its byproduct is A minus lambda I into vector x is equal to 0, and to find the eigenvalues we have determinant of A minus lambda I equal to 0. So this equation we use to find the eigenvalues, and these two for the eigenvectors. Now what is the question here? The question is we have given the matrix A and we need to check out of these four vectors which one is the eigenvector. So we have two options. The first one is the first option. This is method number 1. Find lambda. So to find lambda, what we have to do? Determinant of A minus lambda I equal to 0. That means you need to solve this 4 cross 4 matrix determinant, compare with 0, right, and then find lambda. Corresponding to each lambda we have total 4 eigenvalues, right? So corresponding to each eigenvalues, using these two equations, find x and check which x, and then select the correct option. But it takes more time. So the question is, do we have any other option? So this method, determinant of A minus lambda equal to 0, is not going to help us. Now let us see whether x equal to lambda x or this will help us. If I use this definition, A minus lambda into x equal to 0, then first I should have information about what is lambda. What is lambda? If I have lambda, then I can find A minus lambda I multiply by x. My x is either this or this or this or this, and check 0. But I have no information about lambda. So I start with this equation, x equal to lambda x. Ax I can evaluate. A I have given. Choose x, x, x and x, and check whether it is equal to some constant into x or not. So our main concentration is on this x and this x, right? Let us start with option A, matrix A into x. My x is 1 minus 2 0 0. So what is the product of these two? 5 0 0 0, 1 minus 2 0 0, which is 5. Then the second row, 0 5 0 0, 1 minus 2 0 0 is minus 10. Then 0 0 2 1 into 1 minus 2 0 0 is 0, and again this is 0. And this can be rewritten as, if I take 5 common, then I have 1 minus 2 0 and 0. Now in place of option A, if you choose option B, 0 0 1 0, then what is my product? My product will be 0 0 2 and 3. If I choose option C, 1, 0, 0, minus 2, then my product A into X will be 5, 0, minus 2, 0. And if I choose option number D, 1, minus 1, 2 and 1, then the corresponding answer is 5, minus 5, 5 and 7. So now see, I have A into X with option A, it is lambda into X. Now here, if you take anything common here, can you convert this product A into X in terms of some constant into again X? So 0, 0, 1, 0 should be the format. So my question is that can you write this into lambda, which is some constant, into 0, 0, 1, 0? Likewise this one and this one, right? So in option number B, C and D, we don't find any scalar for which we can convert A into X equal to lambda into X. So what is my answer? That for lambda equal to 5, X is equal to lambda into X, and this X is the eigenvector. So my answer is option number. So actually what we are doing, if I have given matrix A, then using the determinant definition we find lambda, and using those lambda by the definition of X equal to lambda X, we find X. So this is the process we do to find eigenvalues and then eigenvectors. But here what we have done, I have given A, I had a few choices of X, then I work with AX and I observe whether A into X is same as lambda into X or not for the different choices of X, right? And this is the actual definition of the eigenvector for the given matrix A. Then for non-zero vector X, if there exists lambda for which A into X is equal to lambda into X, then we can say that lambda is an eigenvalue and X is the eigenvector. Now let us revisit some important concept of the eigenvalues and eigenvectors. The definition X equal to lambda X. Then suppose I have given the matrix of order n, then it has total and eigenvalues. Some of the eigenvalues are real, some of the eigenvalues are complex. Some of the eigenvalues may be repeated, sometimes they may be non-repeated. All the eigenvalues are distinct. Next, you know this thing. Suppose you have given any matrix A, and if the determinant is non-zero, then all the eigenvalues are always non-zero, and which has the relation with rank also, that rank of the matrix is n. Now suppose some of the eigenvalues are 0, means the determinant is always 0, and once the determinant is 0, the rank of the matrix is always less than n. Next, suppose I have matrix A, the eigenvalue lambda and the eigenvector X, then what can I say about the eigenvalues and eigenvectors of A raised to n? Lambda raised to n. Lambda raised to n is the eigenvalue of A raised to n, and there is no change in the eigenvector. But when I am talking about only lambda, lambda may be 0, lambda may not be 0. Lambda equal to 0, I know that inverse does not exist. That means I cannot talk about A raised to minus 1, minus 2, minus 3, minus 4, minus 5 and so on. That means n cannot be negative. So this is true for n belongs to n. But suppose I am saying that if lambda is not equal to 0, that means now inverse is possible. So all the negative power of A exists, right? And therefore for n belongs to Z, this relation holds. The next, K into A, where what is K? Don't think K is only real. K may be complex also, because some of the eigenvalues may be complex, that we know. So what is the eigenvalue of k into a? K into lambda, and again there is no change in x. We have given the transformation alpha a plus beta into identity of order n, where alpha and beta are constants, complex numbers, maybe. Then what is the eigenvalue? Alpha into lambda plus beta, and again x is the eigenvector. So once I have the eigenvector corresponding to lambda, there is no change in the eigenvector, but the eigenvalues will be different. You might have idea about two more relations. Determinant of A is equal to product of the eigenvalues, and trace of A is sum of the eigenvalues. You know how to find determinant of A, but what is the trace of A? The sum of the principal diagonal elements of the given matrix, and that is same as the sum of the eigenvalues. This was the review about the eigenvalues and eigenvectors which has relation with the given matrix A. I hope you like this video.